So today we're going to do part 2 of our trigonometry lesson. We're going to talk about two special right triangles, the 45-45-90 triangle and the 30-60-90 triangle. First up, we'll talk about the 45-45-90. So when you have this isosceles triangle, two angles are the same and two sides are the same. The easiest number to work with is 1, so I'm going to label both of these legs 1, and then I can use the Pythagorean theorem to see that 1 squared plus 1 squared equals the hypotenuse squared, and we would get that the hypotenuse is the square root of 2. Using my right triangle trigonometry from part 1, I can see that the sine of 45 is the opposite over hypotenuse, or 1 over the square root of 2. Multiply the top and the bottom by the square root of 2, and I get the sine of 45 is root 2 over 2. For the cosine of 45 degrees will be adjacent over hypotenuse, which gives us 1 over root 2. When we rationalize that, we get root 2 over 2. And the tangent of 45 will be opposite over adjacent, which is 1 over 1, or 1. And so from that, we can get the ordered pair that goes along with 45 degrees from the unit circle, x comma y, or cosine comma sine, root 2 over 2 comma root 2 over 2, which I have written right here. Now let's look at this equilateral triangle. It's actually equiangular when all three angles are the same, but it turns out an equiangular triangle is also equilateral, so all three sides are the same. I'm going to end up cutting this triangle in half. So since all three sides are the same, I'm going to call them 2, 2, and 2. So when I cut 2 in half, I get 1. So when I do that, when I draw this perpendicular bisector right down, I end up with this perfect right triangle with a 90-degree angle here. This corner angle is still 60, but I cut this angle in half here, so that's 30. This hypotenuse right here is still 2. I cut this base in half, so this is now 1, and using the Pythagorean theorem, you can solve for this other leg to get the square root of 3. Based on this, we can see that the sine of 30 will be opposite over hypotenuse, or 1/2. The cosine of 30 will be adjacent over hypotenuse, which is root 3 over 2. And the tangent will be opposite over adjacent, which is 1 over root 3, which gives us root 3 over 3 when we rationalize it. Taking this as the x value and this as the y value, you can map this to the ordered pair on the unit circle for 30 degrees, which is root 3 over 2 comma 1/2. And we can do the same thing for 60 degrees right here. Sine will be opposite over hypotenuse, which is root 3 over 2. Cosine will be adjacent over hypotenuse, which is 1/2. And the tangent will be opposite over adjacent, which is root 3 over 1, or root 3. And using this as our x value and this as our y value, we get the ordered pair off the unit circle, 1/2 root 3 over 2. So now, given any circle where the radius is not actually necessarily equal to 1, we can find our other trig functions as follows. The sine will be y over r. The cosine will be x over r. The tangent will be y over x. And I'm going to show you right here, tangent, which is sine over cosine, would be y over r divided by x over r. Dividing by a fraction will multiply by the reciprocals, and the r's cancel. So I wanted to show you that tangent has no basis whatsoever on the radius of the circle. The secant is the reciprocal of the sine, the cosecant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent. Now, one thing I want to note, this is a circle that's going to be centered at the origin. You can draw any ordered pair you want in the entire world, and touching that ordered pair, you will always be able to form a circle centered at the origin. And when you do that, the center is 0, 0, and the equation of the circle is x minus h squared plus y minus k squared, where h and k are the origin, equals r squared, which is the radius. But since we're centered at the origin, h and k are 0, so no matter what, any ordered pair, you can always draw a circle that goes through that ordered pair centered at the origin, where it'll be x squared plus y squared equals r squared. Now, the radius of a circle is a distance, so you got to note that distances are always going to be positive, so this r value will always be positive. Keep that in mind. So for example, if we wanted to evaluate all 6 trig functions for this following here, this central angle that I drew right here for this random ordered pair, -3, 4. Well, using the equation of the circle we found here, that the x value squared plus the y value squared will give me the radius squared, I get -3 squared plus 4 squared equals r squared. which gives me 25 as r squared. Now, whenever you solve for r here and you take the square root to solve, you have to take plus or minus, so we get two answers, positive 5 and negative 5, but we just said r is always positive, so r is going to be equal to 5. Now that we have our x value, negative 3, our y value of 4, and our r value of 5, we can use these formulas right here to find the 6 trigonometric functions. The sine is going to be the y value over r, 4 over 5. Once you have the sine, it's really easy to get the cosecant. It's just going to be the reciprocal, 5 over 4. The cosine is the x value divided by the r value, negative 3 over 5. And once you have the cosine, the secant's really easy. It's just the reciprocal, negative 5 over 3. And the tangent is going to be the y value over the x value, so that'll give 4 over negative 3, or negative 4/3. And once you have the tangent, the cotangent's really easy. It's just the reciprocal, negative 3 over 4. Now, I just rewrote these here, so we had them on the board here for this slide. Remember, your sine is y over r, your cosine is x over r, your tangent is y over x, and r is always positive. Now, we've said you could do this for any ordered pair that you want on the entire two-dimensional plane. Every ordered pair that you are to graph will fall into one, unless you're on an axis, and that's a different story, and we'll get to that, but will fall in one of these quadrants, quadrant 1, 2, 3, or 4. If you're in quadrant 1, then your x value is positive and your y value is positive. And if you're in quadrant 2, then your x value is negative and your y value is positive. If you're in quadrant 3, both your x value and y value are negative. And if you're in quadrant 4, your x value is positive and your y value is negative. So looking just at sine, cosine, and tangent, I'm going to ignore their reciprocals for now. Just looking at sine, cosine, and tangent, if you're in quadrant 2, let's say, let's just look at quadrant 2. The x value is negative and r is always positive, and the y value is positive and r is always positive. So for y over r, you get a positive over a positive, so the sine is going to be positive. Here, you get a negative over a positive, so in quadrant 2, the cosine will be negative. And then y over x will be a positive over a negative, so the tangent is going to be negative in quadrant 2. And you can do that for each one of these quadrants. You can figure out the SIGN sign of any angle in quadrants 1, 2, 3, and 4 based on that way that we just did it. And when you put it all together, it'll follow this thing here. And a lot of students refer to this as all students take calculus, or all-star trig class, or Alvin, Simon, Theodore, the Chipmunks. And we're just talking about your 3 trig functions here, sine, cosine, and tangent. And what the A means, A stands for all. All trig functions are positive in quadrant 1. The S stands for sine. Only the sine is positive in quadrant 1. Cosine and tangent are negative. In T, for quadrant 3, T stands for tangent. Only the tangent is positive. Sine and cosine are negative. And in the 4th quadrant, C stands for calculus. Stands for cosine. Only the cosine is positive. Sine and tangent are negative. Now, as far as their reciprocals go, if the sine is positive, then the cosecant will be positive. And if the sine is negative, then the cosecant will be negative. So we just set this up based on sine, cosine, and tangent. And from there, you can figure out their reciprocals. Now, let theta be an angle in standard position. Its reference angle, which is denoted as theta prime, is the acute angle formed by the x-axis and the terminal side of theta. Your reference angle is always going to be formed by the x-axis and the terminal side, never, ever, ever the y-axis. Now, what does it mean to be acute? Most people say acute means it's less than 90 degrees, but you got to be careful with that, because negative angles like negative 100 is less than 90, but it's not acute. So an acute angle has to be positive. So we've got to know that it's between 0 and 90, or 0 and pi over 2. So this reference angle is always, always, always going to be a positive angle. All right, let's look at some reference angles. Let's just look at a couple examples. If you want to find the reference angle for 325 degrees, well, the first thing you want to do is draw 325 degrees. You can see that it's going to be in quadrant 4. You don't have to draw it exactly. You don't have to get a protractor and figure it out. You just need to know what quadrant it's in. Well, if you label this 0, 90, 180, 270, and 360, 325 is between 270 and 360, so we can see it's in quadrant 4. So now to find the reference angle, it's always made up of the x-axis and the terminal side. So here's the x-axis and the terminal side, and it's the acute angle right there. And now every time you do this, the formula is going to be a little bit different. You have to look at the picture to figure out how you can find your reference angle. You need to see how the original angle theta and the reference angle are related, and it will have some sort of a relation to an x-axis angle like 0, 180, or 360. So you can see if you go around theta plus theta prime more, you would have done one full rotation around the circle. So theta plus theta prime is 360 degrees. Well, theta was given to us as 325 degrees, and you can solve for theta prime to get 35 degrees. Not so bad with degrees, but now let's look at it in radians. Let's do theta equals 7 pi over 5. So again, the first thing you have to do is figure out which quadrant your angle is in. One way to do it is just convert it to degrees, which we talked about in a previous video how to do. You can just plug in pi equals 180, do 7 times 180 divided by 5. Or you can say, okay, this is 0, which is 0 pi. This is pi over 2, which is 1/2 pi, which is 0.5 pi. This is pi, which is 1 pi. This is 3 pi over 2, which is 1.5 pi, and then this is 2 pi. So then this 7 pi over 5 is 7/5 pi, and 7 over 5 is 1.4. You can see that 1.4 pi lies between 1 pi and 1.5 pi, so we realize it's somewhere in quadrant 3. Again, you don't have to draw it exact. So now using the x-axis and the terminal side, theta prime is going to be the smaller of the two, that reference angle right there. So now we need to figure out how are theta and theta prime related. Well, if I go theta, but then I back up theta prime, I end up right here at 180. So theta minus theta prime equals pi. So I can subtract that 7 pi over 5, and I get negative theta prime equals negative 2 pi over 5, divide by negative 1, and I get that theta prime is 2 pi over 5. Another way you may see is if I went pi plus theta prime, I would have done my entire green angle. So pi plus theta prime equals theta. And so then you can plug in that theta is 7 pi over 5, subtract pi from both sides, and you would still get 2 pi over 5. So there's different ways of mathematically being able to calculate what your theta prime is. So let's look at this one. Theta equals negative 2 pi over 7. So this is a negative angle, so I'll set it up as 0, negative 0.5 pi, negative 1 pi, negative 1.5 pi, negative 2 pi going clockwise. So negative 2/7 is about negative 0.29, so that's going to be between 0 and negative 0.5. So it's some angle going clockwise in quadrant 4. Well, now you can see the reference angle is the same angle, except it's going counterclockwise. So theta prime is going to be the absolute value of theta, which is going to be positive 2 pi over 7. So that's how you find your reference angle. All right, well, here's a little fact for you, and this is really important. The absolute value of the sine of any angle will give you the sine of its reference angle. Same thing, the absolute value of the cosine of any angle will be the cosine of its reference angle. And the absolute value of the tangent of any angle will be the tangent of its reference angle. Same thing for its reciprocals. So let's take a look at this on a circle, right? We have some random x comma y, and you've got this central angle theta in here. Well, for example, you can see that the sine, based on the definitions from earlier, is y over the radius r. But we're in quadrant 2, so for like the cosine would be x over r would be negative. Well, this reference angle right here, theta prime, forms a little right triangle where this hypotenuse is the radius, this is the x value, and this is the y value. But this is a triangle, and the triangles have lengths, so the legs are positive. So you take the absolute value of those values, and r is always positive. Now, when you take the sine of theta prime, it's going to be the absolute value of y over r, or the absolute value of y over r. That's where this comes from right here. You can turn them into little triangles. Let's tie everything we've talked about together, and we can use this to be able to define the rest of the unit circle. So put your unit circle aside, don't look at it for now, and then we'll use it to check. Without using your unit circle, how could we find the sine of 4 pi over 3? Well, 4 pi over 3, let's find its reference angle. 4 pi over 3 is going to be in the third quadrant. Here's its reference angle. And you can see that pi plus theta prime would give me 4 pi over 3. Subtract pi from both sides, and I get theta prime, that should say theta prime is pi over 3. Now, from what fact we just went over up here, we know the absolute value of the sine of 4 pi over 3 is the sine of pi over 3. We just use those special right triangles to see that the sine of pi over 3 is root 3 over 2. So the absolute value of the sine of 4 pi over 3 is root 3 over 2. So that means that the sine of 4 pi over 3 is either positive root 3 over 2 or negative root 3 over 2. Well, 4 pi over 3 is in the third quadrant. The sine is negative in the third quadrant, right? Only tangent is positive there. So that tells us that the sine of 4 pi over 3 is negative root 3 over 2. Let's do another one. The cosine of 3 pi over 4. 3 pi over 4 is in the second quadrant. I can see theta prime right here. Put those together. Theta plus theta prime is going to give me pi. Solve for theta prime, and you get theta prime is pi over 4. The cosine of 3 pi over 4 is going to be the absolute value of the cosine of 3 pi over 4 is going to be the cosine of pi over 4, and we just use those special triangles to see that the cosine of pi over 4 is root 2 over 2. So now we know the cosine of 3 pi over 4 is either going to be positive root 2 over 2 or negative root 2 over 2. Well, 3 pi over 4 is in quadrant 2, and the cosine is negative, so the cosine of 3 pi over 4 will be negative root 2 over 2. I'm going to pause here for now, and then we'll do the second half of these notes in another video. I think you need a break.